Hey guys, this circuit that you're seeing here is my little one-day hobby project. So this circuit is aimed to help kids learn the trigonometric ratios as well as get a little basics about digital electronics or how digital logics work. So I've got three inputs: opposite, adjacent, and hypotenuse, which are the sides of a right angle triangle. And then there are the trigonometric ratios indicated by these LEDs. There is the combinational logic and as well as some amount of sequential logic. So let's go into a little bit of basics. In a right angle triangle, the angle opposite to the right angle is called the hypotenuse. The angle opposite to the dedicated angle is or the angle under inspection is opposite, and the side adjacent to that angle other than the hypotenuse is adjacent. So hypotenuse is the longest side of the right angle triangle. Then by taking the ratios of these sides or the combinations of these sides give these trigonometric ratios, which is sine, or the sine theta is the ratio of opposite to hypotenuse, cos is the ratio of opposite to hypotenuse, adjacent to hypotenuse, and the remaining ratios are just like formed by taking the ratios of these sides. So tan is opposite to adjacent, and cosec, secant, and cot are just the reciprocals of these three ratios in the beginning. So cosec is hypotenuse by opposite, and so on. So this circuit contains 3 inputs and 6 outputs. Thinking from an electronic point of view, in the beginning I thought this problem statement was quite easy because all you have to do is like click buttons and the particular LED just turns on. So thinking about sine, it would be opposite and hypotenuse. If I connect these two in series, these two switches, these are just on off switches, so on and off. So I can just connect these two in series, and then once I click opposite and hypotenuse, the sine will just like turn on because that will form a circuit. And to get cos, I would just click adjacent and hypotenuse, and these two might be in series, and then it will turn on this LED. Tan will turn on if I do opposite by adjacent, and connecting these two in series, I'll get the tan LED to glow. The problem arises with these three trigonometric ratios. So cosec, in order to get cosec, I need to do hypotenuse divided by opposite. However, I'll be pressing the same two push buttons which I pressed for sine. So connecting these two in series would just turn on sine no matter how I push this button. So if I push hypotenuse by opposite or opposite by hypotenuse, it'll just turn on sine but not cosec. So I came to know that using like a normal switches and just connecting series or maybe something else might not work. So what I thought about is maybe I can connect a fourth switch which I'll turn on when I want to light these three, but then that will be a kind of it won't be that effective, because then it will be like other than these three buttons or three ratios, I'll be clicking another push button which will be something which will deviate from the trigonometric ratios. This little momentary button, this is not a on off button, it's just I just like go on clicking, it's just a monopulse. So this button is actually used to just output whatever we have given. So if I do opposite and hypotenuse and I click this button, I get the particular ratio. That's actually this process is what I do for each and every time I select a particular ratio maybe. But the fourth button, if I would use for selecting like cosec, sec, or cot, that would be kind of not so interesting and very much like a dull circuit, and there would be like completely no interest in making that circuit. So what I did was obviously if I use something like a combinational logics, what combinational logic defines is that the output of the circuit depends on only the present input, or the present output depends on the present input. What that means is, once I click hypotenuse and opposite, and then once I click this push button, it'll just take whatever it gets. Like after I push the button, it'll just see that its opposite and hypotenuse are on. If in binary, if I'm trying to see that is 101, which is phi, I'll just take this phi and just do whatever with it. Now if I turn on hypotenuse first, then opposite, and then if I click the button, then it'll again take phi and again give me the output which was like supposed to be given for phi. So sine will be phi, cos will be phi, which is obviously not possible. I can't assign two LEDs with the same maybe input or maybe number. Either both will turn on or only one will turn on and the other won't. So such kind of situations will obviously occur. So I had to redefine my problem statement wherein the output depends on the present as well as the previous input. So if I'm doing hypotenuse by opposite, that would mean that my present input, or my the input at the moment, is opposite, but the previous input was hypotenuse. So my circuit will take the readings for opposite as well as hypotenuse. Basically, a circuit whose output depends on present as well as previous inputs is known as a sequential circuit. So I had to go through sequential logic. So over here I've used certain ICs. These are all realization ICs, and this circuit is not minimal. It is a very crude circuit. So obviously you can think of very much optimal designs which can avoid all of these ICs. Maybe we can make use of only 3 or 4 ICs and we can build the circuit, or maybe 2. There can be much simpler versions of this logic, obviously, but since I had to spend only 1 day for this circuit, I mean I had to solder everything and all, and I was much excited to solder because I'm building a circuit after a really long time, that I didn't look much into the circuit part. So however, the circuit works, and I can demonstrate, but let me just point out the ICs that I've used. So I've used 2 NOT gate ICs that are the hex inverters. It contains 6 NOT gates. The IC number is 7404. I've used a decoder, that is a general purpose 3 to 8 decoder, 74138 IC. A decoder is nothing but a circuit which I mean the general purpose decoder is the one which takes in some binary value, maybe say 5 or 6 or 7, and then turns on that particular the particular output. So it has 3 inputs and it has 8 outputs. So 3 inputs are the binary values 0 0 0 0 0 1 up to 1 1 1, and the outputs are named from 0 to 7. So suppose I want to turn on the 7th output, I'm just going to give a binary 1 1 1 to its inputs. So that's basically how it works. So this decoder I've used to turn on these LEDs, and by clicking these buttons I'll be defining some binary values which will be ultimately given to this particular IC, and it will turn on that particular output, which will be useful to turn on these LEDs. The problem was that in a hurry I just I shorted all the cathodes of the LEDs, a general practice, and I took the anodes of the LEDs through this 470 ohms resistors, and I just kept this part of the circuit. I kept this part of the circuit as it is. The problem was that this IC is an active low output IC, in the sense, if I'm saying an output is active, it means that output has a value of 0, rest all have 1s. So suppose if I'm saying 7 is active, then output pin 7 will output a value of 0, and remaining all the pins will output a value 1. So if I give that 0 value to the anode of the particular LED, then it will be completely useless or pointless, because I'll be connecting the cathode to ground, and the anode will also be connected to ground through this resistor, so it will be useless, and remaining all the LEDs will turn on because rest all outputs will be high or 1. So that's what made me use this NOT gate 7404, which I essentially just inverted the outputs which were coming out of this and gave it to these LEDs. And these ICs over here are just 555 timers. Yes, all of them are 555 timers. 1 2 3 4 5 5 555 timers. And then there is 74173 quad D flip-flops. This is just an IC which contains 4 D flip-flops. It can store 4 bits of memory. It has a few essential pins like output enable. Then there are like, this is a tri-state IC, which means it can give high impedance outputs, but that is not necessary in this particular problem statement. There is a clock input to this IC, which is given, the clock is given from this particular monopulse button. Clock is just a pulse or a signal which will indicate this IC to take the inputs and then store those inputs and like give out those, produce those outputs. Suppose the inputs are 0 1 0, then the inputs will not be accepted by this IC until I click this clock. Once I click this clock, the IC will accept those inputs and then just transmit those inputs to the output. This is what I've used, because see, suppose I've just clicked hypotenuse. Okay, I've just clicked hypotenuse, then I've not clicked the remaining two buttons. Then the output will be unpredictable. Like, what is hypotenuse? I need to click some other buttons, right? If I just clicked hypotenuse and I just left the other two buttons, then at that instant the problem will be the outputs will be like kind of unpredictable, or I need to again define those outputs. So that was a problem. So hence I just give a control signal. Hence once I've done pressing hypotenuse and opposite, once I click it, then it will show me cosec. So that's why I use this clock pulse and this D flip-flop. Then I have another NOT gate, and there is 7410 3 input NAND gate, and then there is the AND gate and an OR gate IC 7408 7432. I used these ICs for performing some of the combinational logic that was necessary in the point of view of this circuit. So there is a micro USB cable for power purposes, and that's all about the external hardware part about this circuit. Let me just power this on and demonstrate to you what's going on. So I'll click these two. Okay, so in order to get sine, I'll just go random so that it shouldn't look like I've connected some kind of maybe a shift register, which I just go on clicking this and it'll just go on shifting. So I'll just start from maybe tan. So tan is opposite by adjacent, and once I click it, I get tan. Now for maybe cosecant or secant, whatever, cosecant, I'll get hypotenuse divided by opposite. So cosecant. To get sine, just look at this. Opposite is turned on and hypotenuse is turned on. For sine, I have to just turn on the exact two buttons, but in the opposite manner, like opposite divided by hypotenuse. I get sine. If I click it in the opposite manner, I get cosec. And for sec, I need to do adjacent. I need to do hypotenuse divided by adjacent. So I'll do hypotenuse divided by adjacent. I get secant. And then for cos, I need to do adjacent divided by hypotenuse. So cos. And then for getting cot, I need to do adjacent divided by opposite, which will give me cot. And for tan, I need opposite by adjacent, tan. So basically I can just get any trigonometric ratios. Like cos, I need to do this. For tan, I need to get opposite by adjacent. For cosec, I need to get hypotenuse by opposite. Sec is hypotenuse adjacent, and cot is just adjacent by opposite. Yeah, so this circuit performs well, and actually didn't expect my crude circuit to perform this well, but it does perform well. And yeah, once I give all the three inputs 0 and just give a clock pulse, everything just resets. So yeah, this circuit works well. And for 111, this I considered as an unpredictable, or what you can say, a scenario which will not occur. I considered this as a don't care. So whenever I give 111, something unpredictable happens. Like, see, right now nothing is on, but suppose if I just put it to some value and then I give 111, okay, sometimes it just produces some particular like peculiar output like caught. So by getting a 111, if I go on pressing it, it just gives me a caught. So usually 111 is something that I didn't account to, because it was not necessary. As opposite, adjacent and hypotenuse, I never take a ratio of all these three sides. So uh, I didn't want to add some more combination logic to avoid this particular condition. So however, this circuit will work perfectly fine. If I want to just reset the circuit, all I need to do is just turn off all these buttons, or just push them out and just press the clock. So the circuit resets. Now let me show you the circuit diagram and also explain a few bits of it. So this is the circuit diagram of it. I'm sorry, this is the circuit diagram of it. Yeah, it's quite big, and over here I've indicated the 555 timers as S bar, R bar and Q. S bar, R bar are the inputs and Q is the output. This is known as an S bar, R bar latch. Now what does a latch mean? So basically a latch is nothing but it's like a push button basically. So if I have, say, a button, okay, a push button, this push button's output, this point, if I've connected this to maybe VCC, this point will have, and this point is GND, this point will have two stable states, which means that at a point of time I can have a 5 volts when the switch is open, and once I close this switch, okay, once I close this switch like this, then this ground or the current will just essentially flow like this, and this point will get a 0. So it can go to 0. Hence this particular point A can exist in two stable states. Once I open the switch it will be 5, and once I close the switch it will be 0. So it will continue to do this until unless I myself give it some kind of an instruction to change the particular output. So basically in a latch, in an S bar R bar latch, what happens is, if I give in an S bar R bar latch, let me draw a small one over here. The bubbles just indicate that they are active low, which means that the particular input gets activated when I give a 0. So in an S bar R bar latch, if I give 0, 1 as the input, I'll get 1 as the output, and this 1 will like sustain itself until unless these two inputs are 0 and 1. If I give 1 and 0 as the input, the output will be 0, and it will maintain this output 0 until unless these two inputs are 1 and 0. In a 555 timer there is a priority to R. So what happens is, if I give both zeros, then the output will be 0, because the R bit, the R input has a 0, which means that if I give 0 to R bar, then it doesn't care about whatever input the S is getting. If 0 is at R, then it will reset no matter what. Reset in the sense the output will be 0. So first of all, what is inside an SR latch, or how is an S bar R bar latch made? Let me just draw a small circuit of it. So so this is what an S bar R bar latch looks like, and let me try to demonstrate what is happening. These are NAND gates. I just written this as NAND. Okay, so if I give a 0 at this input, okay, I have to assume some particular state at the output, which means that once I turn this circuit on, then the output will be something, like something, it has to be something. So suppose if I assume it to be 1 0, okay, as the output, what will happen right now? This 0, okay, okay, leave the 0. This one, I've given a 1 over here. This one will just appear at the input of this NAND gate, and 1 1 as the input of NAND gate, the output will be 0. And in a NAND gate, if one of the inputs is 0, regardless of the other input, the output will be 1. So if the present output was 1 0, then the next output will be 1 0 as well. If I assume the present output was 0 1, what will happen to the next output? So this 0, obviously, it regardless of the other input, this will just make this 1, and this one will appear over here, and this one will, and this one and this one will make the output as 1. So I mean this one and this one will make the output as 0. So no matter what is the present state, the output will be 1 0 if I give 0 and 1 as the input. I can draw a small function table to much clearly specify what is happening. So in a 555 timer, if I give 0 0 as inputs, the output will be 0 because R has a greater priority. Whereas in a normal S bar R bar latch, if I give 0 0, the output will be 1 and the state will be, I mean, even the complementary output will be 1, so the state will be unpredictable, because it's not even like, you can't even call it to be set, you can't even call it to be reset. It will be like, you can't predict in what state it is. It's neither set nor reset. If I give 0 1, the output will be 1 0, which indicates it is set. 1 0 will just reset it. So just focus on the Q column, because Q bar is just the complement of this, in the sense the inverse of this. If this is 1, this is 0. That's what I'm trying to indicate, that if the outputs are 1 1, then the state will be unpredictable. Next is 1 1. So what happens when I give 1 1? If I give 1 1 over here, then if suppose this the initial state or the output was 0 1, then this 0 will just appear here and the output will be 1, and this 1 will appear over here, and with the inputs 1 and 1, this NAND gate will produce an output 0. What happens is, whatever the output is, the same output will be produced when the inputs are 1 and 1. So basically this S bar R bar latch enters no change state. So whatever the present output was, the same output will be there in the next output. So these plus signs just indicate that this is the next output. So this is known as the no change state. This is the reset state, this is the set state, and this is the unpredictable state. So this is basically how an S bar R bar latch works, and this particular S bar R bar latch is already present in a 555 timer IC. Now how to convert a 555 timer IC into an S bar R bar latch? First of all, you need to look at this circuit diagram, maybe pause the video and take a snapshot. Just get this. This part of the circuit is not much necessary, it is just how the LEDs are connected from the switches. So this part is necessary, and these trigonometric ratios are basically connected to the LEDs. So it is connected something like this. You can take it is connected something like this. All of them are connected like this. I essentially connected it in reverse mode, and I mean in the reverse, and that's why I had to use a NOT gate to invert these. However, I could use much better options, but I I just didn't want to spend a lot of time, and I just had a NAND Gate lying around. So yeah, now the first challenge is how to convert or how to use the S bar R bar latch present inside a 555 timer. For that, I'd like to draw the circuit diagram of how to convert or how to use the S bar R bar latch in a 555 timer. So this is a 555 timer circuit. The block diagram of 555 timer. This is GND, and this pin is VCC pin 8. Pin 2 is known as the trigger, and pin 6 is known as the threshold. Pin 7 is the discharge pin, which won't be necessary in this case because I'm not connecting a capacitor. Pin 3 is the output. Pin 4 is the reset. So the reset of the S bar R bar latch is already present at this particular pin, so we don't need to do anything more. The trigger pin is nothing but the S bar, essentially the S bar, and this is nothing but the R bar. The only thing is we need to connect the threshold to ground. This is the only modification that needs to be done in a 555 timer in order to access the S bar R bar latch, and it is very much advantageous because R bar has a greater priority. So 0 0 will not give an unpredictable output, it will just give 0 as the output. This is the output. S bar R bar are the inputs. This can be just ignored. These two can be just ignored. This is just the control pin which gives control to the internal potential divider, but this is not much necessary, and 7 is also not much necessary. However, we could connect a 0.01 microfarad capacitor from here to ground. However, if that is not connected, it won't produce much of a problem. The only problem would be stability cases, but here I don't think it will be producing any sort of a problem. There is no capacitor, hence no need of this discharge pin. This is GND and this pin is VCC. So this is basically the circuit to obtain S bar R bar latch from a 555 timer. I've used 555 timers and I didn't use any other ICs, is because 555 timers are very cheap, and if I'm buying a lot of them, then I get it for much cheaper prices, and it has a much it has an advantage that reset is having a greater priority. So these S bar R bar latches are basically these 555 timer circuits that I've connected over here, all of them. And to demonstrate, let me just rig up a 555 timer and demonstrate how the S bar R bar function works. Got my breadboard over here. I tried to rig parts of this circuit earlier, so there are some of these wires connected over here to the VCC and GND rails. So first off, in order to access the 555 timer's S bar R bar latch, we need a 555 timer IC to get this in focus. This is the NE 555 timer, so I'll connect it over here in the breadboard. So as you can see, pin 8, that is VCC, is connected to the positive rail, and the GND, that is pin 1, is connected to the negative rail via these copper wires. Next I need to do is connect pin 6, which is threshold, to ground, so that pin 6, actually when pin 6 senses a voltage greater than 2 by 3 of the VCC, that is 2 by 3 of the 5 volts, then the output will be off, which means that if the voltage at this pin number 6 goes above 66% of whatever VCC voltage we are giving, then the output will be turned off. So we don't want the output to be turned off because of this pin, so we tie this pin to ground so that the output would never be turned off because of this pin number 6. Next we need R bar, which is directly this pin number 4, which is reset, connected somewhere here. Then I need S bar, which is essentially pin number 2, which is the trigger pin. The trigger pin would just turn on the output when it senses an input less than 2 by 3 VCC. Here VCC is always 5 volts, so sorry, less than 1 by 3 VCC. Here VCC is 5 volts, so 1 by 3 VCC would be 5 divided by 3, which would be 1.66 volts, which is quite the amount of, which is obviously anything less than 1.66 volts is a 0, so that's cool. Next, I'll just connect 2 momentary push buttons. So these are just push buttons, they don't have any on and off, they're just momentary. There are C-shapes, so C-shaped notches over here below the pins, which indicate that the pins along this C are actually connected, which means that these 2 pins over here are connected together internally, and these 2 pins are also connected together internally. Once I press this push button, these adjacent pins get connected. So these 2 adjacent pins are normally open, and when I close them, they both get connected. Keeping that in mind, I'll connect this push button over here, and the next push button would go here. Okay, yep, that's it. Now I need to pull up these points, so I'll pull it up by using a 1 kilo ohm resistance. You can use anything like 1 kilo ohms to 10 kilo ohms, maybe 15 kilo ohms as well as pull-up resistors. I'm using 1 kilo ohms because that's what I have right now. Okay, so next I'll connect the output to an LED. So I have this red LED, and its cathode will just go to the ground. Okay, so that's it. Now let me just power this up. So this is the VCC rail and this is the GND. Okay, so in order to set it, all I need to do is push this button, which obviously okay, I've connected should have connected set over here into set over here, so yeah, that was the misconnection. So now resetting is just, if I click this button it will reset, and clicking this button will set it. So set, reset, set, reset, that's it. So once I set it, it's set completely, in the sense I don't need to do any further action, and it'll just remain in this set state, or its output will always be 1 until unless I come back and I then press this reset button. So this is basically the S-bar R-bar latch. So this is how you essentially use the S-bar R-bar latch of the 555 timer. Now I wanted to demonstrate what happens when you use like inputs like a 0 0. Right now the inputs are 1 1, so it's in no change state, which means that the output will remain what its previous output was. In the sense, the output will be same as that of the previous output. So right now the output is 0 because it is going to stay 0, and its next output is also going to be 0. However, if I give 0 0 as the input, so 0 will set it and 0 is set. So in any order if I give it, it will just give an output 0. once I give 0 0 as inputs. So that's a good thing about the triple flag timer, as it avoids that indeterminate state, or maybe we just don't require that one in this particular circuit. So rest of the circuit is over here, which is pretty much simple to understand in the point of view of digital electronics. There are 3 input NAND gates which I've used over here. What this does is, when the inputs, all the 3 inputs are 1 1 1, we have to we need to emphasize that when the switches are closed, the input that we're giving is 0 actually. Okay, once I close the switches, the input is 0, and once I open them, the input is 1. So if all the 3 switches are open, then these 3 pull-up resistors will pull these inputs to 1. So 1 1 1 as the input will just produce a 0 as an output of this IC. This 0 will just essentially reset each and every flip-flop that is there. So it'll go on resetting this. All the 5 triple flag timers will reset, in the sense all the 5 will output a 0 at the output. Now since all 5 are resetting 0, obviously the output of these these OR gates are going to be zeros, and hence this 74173 IC, once I give a clock from this push button, once I give it, it'll just store 0 0 0, and that 0 0 will be passed on over here. This 0 0 0 will be decoded by the decoder, and this Y0 will go to 0, but it is an ignore bit, so that completely it's ignored. The main point of adding a NAND gate over here is to reset the entire circuit once I give an input of an input of 1 1 1 over here, which will eventually get converted to 0 0 0. So giving any other like supposedly, okay, now how is this circuit capable of solving the problem of the present and previous inputs? So if I want to give sign, what happens is, once I close this button, which indicates opposite, the 0 will be this point will be 0, and this 0 will also appear at the input of this AND gate. So it'll appear over here, and once the input of any one input of the AND gate is 0, its output will be 0. So this AND gate will just reset this particular IC. So this IC will reset. Next, this same 0 bit will appear over here at the output of this NAND gate. So the output of this NAND gate will be 1, because if an AND gate has any of its input as 0, its output will be 1 regardless of other inputs. So 1 at the S bar is just asking S bar to disable, in the sense what will happen is, this reset will obviously be 1, and this set will also be 1. So output will be just 0, as we saw in the triple flag timer. Output will be just 0. So if I press, if I'm trying to get sign, then I'll just press opposite, and I'll press hypotenuse. Once I press opposite first, this and these ICs will be kind of disabled. This won't be disabled, but it's like its input itself will be disabled. So it's like practically saying that this IC is disabled. So these two ICs will be disabled. So by clicking opposite and hypotenuse, I'll just get 1 0 0 as the output. So I'll get 1 0 and 0 as the output, and these outputs will be taken over here, and obviously eventually after all the combinational logic, I'll get 1 0 0 over here as well. Once I give the momentary push, or once I give the clock pulse, clock trigger, this 1 0 0 will be loaded inside the flip-flops. I'm just using 3 of the D flip-flops. Then the same thing will be outputted 1 0 0, and the fourth one, which is sign, which is Y4, will be activated. Next, if I'm trying to go for cosec, so first all the three are going to be zeros. I mean, all the three inputs are going to be ones, and everything will be resetted. Now once I just cosec is nothing but hypotenuse divided by opposite. So first I'll close the hypotenuse switch. Once I close this switch, I'll get 0 at this point, and then what will happen is, first off, once I get 0 over here, these two ICs will reset, because this 0 will appear at the input of these this AND gate, and its output will be 0 for both of these ICs, as they have a common reset. So both will be resetted. So this will reset and this will reset as well. Next, what happens? After I pressed hypotenuse, I need to press sine, right? So I press this bit, that is sine bit. Once I press sine, what happens is this will get set. So I'll get 1 0 1. 1 0 1 is 5 in binary, and same 5 will, after these combinational logics, since these two will be resetted, you'll get 0 and 0, and an input of the AND gate is, being 0 is, the output will be 0, and these two OR gates will just produce 0 0. So these two OR gates will 1 and 0. This OR gate will produce a 1 because this output is 1, so 1 will just produce a 1. Over here, this is from the second IC, so this has a 0 and this has a 0 as well. Both the inputs are 0, so output will be 0, and this OR gate has an input from the output of this third IC, so which is 1. So I'll get 1 0 1 at the inputs of the D flip-flops. Then I give a clock pulse, and the 1 0 1 will be stored inside the IC and it will be outputted. Now 1 0 1 indicates 5 in binary, which is Y5, and Y5 is cosec. In the same way, the circuit can be used. The circuit also selects cot, cos, sec, sine, cosec, and tan. All of these will be selected in the similar manner. When one will be selected, something will be resetted in the entire circuit, and whatever the final output is going to be over here at the output of these three OR gates, and that is what is going to be reflected at the output from this decoder. So that's it. Like, share and subscribe, and thanks for watching.